You are hours into a complex coding session. You compile the software to test a new feature, and the entire system crashes. The functional code you had 10 minutes ago is gone, overwritten by a fatal error. A standard backup is useless here. You need a way to sharply rewind the active state of your project. Without a dedicated system, developers rely on the digital equivalent of hoarding. We copy and paste the same document repeatedly, appending desperate labels like V2 or actual final to the end of the file name to map out what worked and when. The fatal flaw in this workflow is human error. The moment you forget to manually duplicate the file and hit save on a broken idea, your safety net vanishes. The defective code overwrites the functional state, destroying your progress. Relying on manual file duplication is an unsustainable way to engineer software. Scaling a project requires an automated engine that systematically archives every historical state of a codebase without requiring the developer to manage it. Today, that engine is Git. It operates silently in the background of nearly every professional software environment, acting as an infallible timeline that allows developers to step backward the exact second a bug appears. The necessity for this tool peaked in 2005, when Linus Torvalds engineered Git to manage the development of the Linux kernel. Thousands of contributors were submitting concurrent code changes to a highly fragmented operating system. Tracking modifications manually across that volume of files had become impossible. Torvalds required a mathematical, foolproof method to isolate and track alterations across the network. Modern enterprise Git is massive, but its core mechanics are straightforward. By reverse engineering those mechanics in C++, we can build Git Lite, stripping away the complex networking features to expose the raw logic that makes version control possible. The first architectural hurdle is storage. We have to map a text file into computer memory so that it can expand dynamically with new data without crashing the program. We solve this using a linked list. We wrap each individual line of text inside a structural container called a line node. This node holds the text, and it also holds a digital pointer that shoots a tether directly to the exact memory address of the next line. Because each block explicitly maps the route to the next one, we avoid declaring a maximum file size up front. We simply attach new nodes to the end of the chain as the user types. To save versions of this fluid file, we implement a stack. This is a rigid vertical array governed by a strict last-in, first-out rule. When we trigger a save, the program compresses our linked list and drops it into the cylinder. As the developer makes new commits, those subsequent versions drop in from the top, piling up and safely burying the older states in perfect chronological order. Combining the infinite flexibility of a linked list with the rigid hierarchy of a stack array establishes a reliable, traversable timeline. These data structures are managed by the file object class. This central engine controls the nodes and directs traffic in and out of the history stack. The most critical operation in this engine is the copy file function. To save a timeline state, it performs a deep copy, generating an entirely independent, physically separate duplicate of the current file data. If the program only copied the pointers, the active workspace and the saved history would share the exact same memory addresses. Any edit to the draft would automatically alter the saved history, destroying the archive. When we need to travel back in time, the engine first executes a wipe command. It safely deletes the active working memory, dismantling the current code one node at a time to prevent orphan data from causing a memory leak. With the workspace cleared, the rollback command takes over. It steps down the history stack, points to the slot below the current state, deep copies that archive data, and unpacks it back into the active workspace. Version control operates entirely on precise logic. The ability to restore lost work is the direct result of disciplined memory allocation and pointer management. To make this engine usable, we scale out to the macroscopic level, the user class. Object-oriented design isolates the data. We assign every user a private array of file objects. Each silo contains its own active code and its own history stack, guaranteeing that one developer's project cannot contaminate another's. Object-oriented programming encapsulates complex memory math behind a secure boundary, providing a clean interface for human interaction. In practice, the sequence is seamless. A user logs into the system, opens a new workspace, and begins drafting lines of code. Satisfied with the logic, they trigger the commit command. The engine runs the deep copy, pushes the bundle onto the stack, and permanently locks that exact functional state into the history array. Minutes later, the user makes a catastrophic edit. They delete a core function, corrupt the architecture, and completely break the file. The user invokes the rollback command. The corrupted memory is wiped, the stack index drops, and the flawless state materializes instantly. We constructed this system entirely from standard C++ components, linked lists to handle dynamic text, stacks to organize history, and object-oriented design to isolate workflows. Mastering these mechanics establishes the exact groundwork needed to build advanced tools like branching code paths and simultaneous merges. The software that secures modern engineering relies entirely on the precise application of basic computer science.